will address 4 topics: NGSS Practice 2, the Modeling and Inquiry Methodology, the Modeling Cycle, and the storyline of an instructional unit that is consistent with this methodology. The Next Generation Science Standards recommends developing and using models as one of the science and engineering practices. Developing and using models means different things in different grades. We will focus on high school science and engineering practices, where the emphasis is on developing models to predict and show relationships among the variables involved in a scientific phenomenon. Briefly then, for a high school curriculum, the word model refers to the scientific model of a phenomenon rather than, say, a stick model of an airplane. A model is developed using data and evidence and may not catch every nuance of the phenomenon. The parameters involved in the phenomenon are brought together in the model, and models may be represented in several ways, typically verbal, pictorial, graphical, or mathematical. In order to apply the modeling methodology, we need to be deliberate in how we address the entire curriculum. When we use an inquiry and modeling methodology to construct a curriculum, the curriculum content is organized using scientific models as units of structured knowledge. Students work together to arrive at these models by doing their own hands-on experiments in a structured fashion. The experiments lead students to collaboratively construct models of the phenomenon and then to describe, explain, predict, and expand on the models that they have constructed. The 3 main features of the inquiry and modeling methodology form a defined pedagogy. A curriculum with this pedagogy needs to be constructed with units that are sequenced so that concepts and skills build on each other in a well-constructed sequence. And of course, assessment must be built in throughout. Thus, the curriculum looks different, and simultaneously, the classroom looks and functions differently from a traditional classroom. The modeling cycle consists of 2 phases: model construction and model deployment. In the model construction phase, students work together on hands-on labs. Each lab typically has 4 phases: a pre-lab discussion, the experiment, and a post-lab discussion from which the model construction takes place. In the pre-lab phase, students interact with familiar objects or simple lab equipment. They make observations, discuss them, make predictions, or figure out measurable parameters. They then design an experiment, share their ideas with the class, and figure out a consensus procedure for the experiment. They then conduct the experiment and take data. In the post-lab phase, students analyze the data and discuss their conclusions so that they can then create a conceptual or mathematical model of the phenomenon. After the model has been constructed, it is time to deploy it. The deployment phase consists of several aspects. Students learn to represent the model using different representations, such as verbal, pictorial, graphical, or mathematical representations. Students do practice problems, which typically employ the multiple representations and involve translating from one representation to another. Readings are included to deepen student knowledge. An application lab typically concludes the unit or cycle. This cycle is repeated if there is more than one phenomenon in the unit or if the model needs to be refined. What does the storyline of an instructional unit look like? Our instructional units in exploring physics start with an exploratory activity, followed by the construction of the model of a phenomenon. Students then use the model, compare and evaluate different models, if needed, and then finally revise the models. The purpose of this sequence is that in the exploratory activity, students connect new ideas to previous experience. Exploratory activities use familiar materials or toys and allow students who have not previously seen those materials to experience them, putting all students in the class on a more even footing. During model construction, students get to illustrate, explain, or predict what might happen. When they use the model, they do so again and get to use representations. Comparing and evaluating different models allows students to look for patterns and develop critical thinking. And finally, revising models allows students to go beyond the first simple model to one with more predictive or explanatory power. The 4 levels of this learning progression give students extensive experience with a given concept, while they are also learning to think like scientists. An example of the storyline for the accelerated motion unit in the Exploring Physics Curriculum app is shown here. In the exploratory activity, students observe the motion of different cars. They then construct the model of accelerated motion with a lab of a car sliding down a ramp and develop the equations of motion. Then they express and use the model using motion diagrams, position time, velocity time, and acceleration time graphs, and the motion equations. Intertwined with using the model, they have reading pages and they use animations and simulations. The basic model is expanded to learn about speeding up versus slowing down, positive and negative velocities, and about calculating displacement from velocity time curves. So, what is special about a carefully constructed storyline? For one, the learning is sequenced. Skills are designed to build on one another and are strategically repeated and intertwined so that student learning is cemented. Second, it avoids pitfalls that might occur from putting together activities from multiple sources, such as gaps in the storyline or tangential asides. One does not want broken threads or flyaway threads in a curriculum, but instead, what one wants is a well-woven rope so that student learning is strong and consistent throughout. Each unit in the Exploring Physics app has been constructed to follow the same basic storyline. All units start with framing questions and a qualitative exploratory activity. They are then followed by a hands-on lab where leading questions are provided so that the lab can be designed and analyzed by students. The model is then used via multiple representations and in practice problems. More advanced labs follow if needed. Readings are available for each concept along with animations and simulations. Models are then revised to expand their scope if needed.